Alrighty, so your programming test 1 will be tomorrow, Williams Small Center. So please make sure to read the whole guide. Just make sure don't miss any important information. Two things to remind. Make sure you bring your photo ID. Without it, you cannot be allowed to write the test, right? Just standard, right? Make sure you got your ID. You will be asked to put all your bags at the front of the classroom, the lab, and also even including your mobile phone. So you're not allowed to bring your phone to your seat. So please make sure you got your photo ID, okay? So we can check during the test. And also make sure you bring your sketch paper. I'm pretty sure you will need it. I don't think it's a wise idea to do everything in your head. Maybe you're capable of doing it, but I wouldn't risk it in the test. So please bring your own paper. I don't think we will be able to provide everybody sketch paper. Please bring your own. All right, so yeah, everything else has been set in the PDF guide, nothing else to add. So just make sure you go over the cover materials and we'll see how that goes tomorrow. 1 hour, okay? So make sure you arrive, when you arrive before we set up the room with the TA. So please wait outside, we'll let you in. Hopefully at least about 5 minutes before the test starts. You can get seated, get yourself comfortable, and then we can get started, okay? All right. Your assignment number 1, of course, solution has been released for your programming test 1 prep. And your assignment number 2 has also been released, right? So if you really cannot do anything before the test tomorrow, it's understandable, not ideal, but you definitely want to get started after tomorrow, maybe after the test. It's actually quite a crucial assignment for you to get right. Otherwise, you definitely cannot really get exactly what's expected for programming test number 2, right? Which is another 15% for your grade, all right? Okay, so I'm going to talk about one of the stuff about how you can test for exceptions. That might be something, I'm pretty sure that's something you learned from 2030, the Java course, but maybe it's been a while. I want to review that part very quickly today, just to make sure everybody at least understand what the JUnit tests are asking you to do. And then after the recap, maybe. Okay, let's do a recap before we move on to that part. So last time, we just talk about the various properties about depth first search. Especially we talk about depth first search on the directed graph. So today, I just want to go a little bit more about depth first search versus breadth first search. There's another searching mechanism, like a traveling mechanism called breadth first search. I want to cover that today. That one should be done pretty quickly. We'll do some simple example tracing. I already got some tutorial video on the lecture site. You can also take a look at the more complicated exercises as well. Okay, I'll get to it. Okay. Right, so when we talk about directed graph for DFS, you have to worry about different colors, different edges, etc. Right, and also the timestamp for D and F. We just spoke about different properties last time, so please go over them. Definitely, they will be covered in your written test and also in your exam as well. Okay, and also, of course, make sure you also understand the correspondence to the stack is also very important, right? But today we're going to see, for another traveling mechanism, traversal breadth first search, we're going to use a different data structure. And you can even take a guess. Symmetrically, it's going to be a FIVO, first in, first out queue. We'll see how that can be done. That one turns out to be actually much more straightforward to be done. But just got to be careful. It's done in a different way. Okay, we'll see. All right, and then we talk about timestamp, especially given the D and F value for a particular vertex or between 2 vertices. Can you judge to see if they are related by each other, maybe by ancestor, descendants, or neither? Right? That's something you want to be very comfortable with also during the assessment. The best way to really understand about what I said last time, which I just give you some example. In general, you want to visualize the intervals about the finish and discovery time. If they overlap, they're somehow, if they're completely, one is completely contained by the other, is ancestor and descendants. If 2 intervals are completely disjoint, they are neither ancestor nor descendants, right? That's a principle, right? So that's something we also said last time. All right, and then we started with reviewing quickly some basics about doubly linked list. So when you actually download the starter code for your assignment number 2, you will see inside the Edge, I forgot exactly the name. It's called Edge Graph Base, something like that, a package. You will see a number of classes over there. Those are the classes you will be given as well in your programming test 2. So get yourself familiar. You'll be given something identical. So it definitely doesn't hurt to actually study them a little bit before you start coding for A2, right? So that's simply one of the methods about remove. And the reason I talk about remove is one of the reasons that you will see inside the edge and vertex class, we actually store a new reference over there to really refer the vertex back to the list of vertices. I kind of briefly said that it's going to for efficiency reason, but exactly how? We're going to see today briefly, right? That's something you also want to link back to 2101, right? First of all, make sure you understand about how to implement the remove method, how to trace it, just understand how it is going to work, right? It's a bigger of 1, constant time, because there's no loop. All right. And then we spoke about the first strategy. Okay, so we'll cover the first one here. First one here will be sufficient for your assignment number 2. Most likely assignment number 3, which is what I did last semester. If I decided to let you guys try maybe 1 or 2 more strategies, I'll let you know. But I'll make sure I cover that before I have you guys do it. Okay, but this definitely is the most fundamental one to really study. Okay. Later on, we are also going to cover another 2 strategies, at least on the paper in class. And then we're going to do some comparison to see how these 3 strategies will differ in terms of the different graph operations. Right? We'll see later. All right, so let's do a very quick recap. I think that's relevant. Okay. So we got a class called edge list graph. And we got 2 generic parameters, one for vertex, the other one for edge. And we got 2 doubly linked lists. One is for vertices, the other one is for edges. So you can think about either one of them can call the remove method that we just spoke about. Exactly how, I'll show you. Okay, I'll give you some example code. Okay? And also we got some Boolean flag just about whether or not the graph is directed. Okay? And then in assignment number 2, you will see that I somehow collapse these 2 classes together into a single class. You know, attributes are really the same, but arguably this could be a better design to split them between 2 classes. But just so, you know, for simplicity reason, I don't want you to deal with so many classes, you know, in the assignment, in the programming test. I kind of collapse them into 1. But you just notice that they are really equivalent. The most important attributes right here. Okay, let's revisit again. Let's say in the edge class over here, sorry, in the vertex class, beg your pardon, okay? In the vertex class, we have an attribute over here called vertex list position. That one there is of type doubly linked node. So that means this is a reference back to some node in the vertex doubly linked list. Right? We'll see exactly how to visualize this. Similarly, you can see under the edge class over here, there's also one attribute called edge list position, which is of type doubly linked node, which means every edge has a reference back to the list of edges that's stored in the graph level. And whenever you want to remove a vertex or the edge, you can simply pass the reference itself, and the removal is going to be constant time. If you don't really have this reference here, removal could be up to maybe a linear time, right? That's something you also learn from 2101, right? All right. Any questions so far? All right, good, awesome. All right, so I'll get to this one here is to deal with exception handling. I'll cover that very quickly. That one just like a brush up to make sure you're okay with A2, right? Let's take a look at the visualization first to begin with, okay? So here is an undirected graph right here, right? You can see we got 1, 2, 3, 4. We got 4 vertices. Accordingly, we have a doubly linked list of 4 vertices. And here, we'll just call it capital V. Okay. This one here. All right. So you can think about the capital V here is the list of vertices. The list of vertices. Right? You can see exactly we got A, B, C, D. And then you can see A, B, C, and D, right? That one's straightforward. But you'll notice that every vertex object also has a pointer pointing back. This reference here is exactly what I just said about vertex list position. Okay, you can make notes right away, right? To see exactly how that works, I'll go a little bit further. Just one moment. All right, let's look at the edges. So we got 1, 2, 3, and 4. 4 edges. Okay, so we got a list of edges of size 1, 2, 3, 4. Right? You can see we got O. Oh, let me do it again. We got O, and then we got P, and then we got Q, and also we got R. Right? Exactly 4 edges. Okay. Let me write it down. So we got vertices, we got edges, but we're going to see exactly how to set the origin and destination in just one moment. So think about this one here will be the list of edges. Separate list. So this one here will be the list of edges. All right? And then you can think about right here, we got different objects right here. So for example, you can see that here, A, B, C, D are 4 separate vertices objects. So these are vertex objects. Okay, when you look at the starter test for assignment 2, we're building the graph in this way, right? You'll see exactly correspondence, right? All right, and then we also got edge objects right here. Let me just use green. Right, you can see we got also 4 separate edge objects here. So these are edge objects. Okay, I'll get to the position reference back in just one moment. That's the tricky part. But let's look at, for example, you can see for O here, it points to A and B, 2 vertices. How come? Because in this graph over here, A here and B here. Because it's undirected, doesn't matter which one's origin, which one's destination. So when you actually write your code for assignment number 2, we assume that it's undirected graph. So you want to make sure your code can deal with edges, either AB or BA, treat in the same way. That's a little bit hints to you when you deal with them, okay? All right, so let me just do some very quick annotation here. So here you can see O points to A and O points to B, right? That's why this is because we got A here and we got B here, right? One is origin, the other one destination, okay? Let's say this one origin and also destination. All right, and you can check the other 3 edges as well. It's set properly. All right, final point to make. What about the two references that will point back? Let's look at this one here. Let's start from this one. Let's look at vertex A. And then you will see that it has one reference pointing back to the doubly linked list. And this one here is the attributes value of vertex list position. Let me point to you one more time. Okay? If you look at the vertex class, it is this doubly linked node. It's pointing back to one position in the doubly linked node, into the doubly linked list. Right? It's called vertex list position. All right. So this one here is the vertex list position of type doubly linked node. So it's pointing to, for example, this particular node in the doubly linked list. Right? Of course, doesn't matter where you are in the vertices. It could be that you're talking about B here, C here, or D here. They all have their own attribute pointing back. All right? First of all, let's identify that. Similarly, you can see for every edge over here, you also have one reference back to the corresponding position in the edge in the list of edges. Right? Similarly. Okay, let me write it down too. So that one there. So for example, you got this object here for edge O, and that one points back to a position in the doubly linked list, which just happened to be the first one. It can be somewhere in the middle, right, in general, all right? And this one here, okay, let's go back again just to see the correspondence. It's called the edge list position, all right? So it's called the edge list position. All right, so that's about the structure, right? You've got to be much aware about how the edge list is going to work. So now the question is, how is this useful, right? Let's say, for example, I decide I want to remove, for example, vertex B. let's say. Of course, it's going to involve about, you got to remove this vertex B from this doubly linked list, right? Part of the step, you got to remove it. And also, you got to remove also the involved edges, O and P as well. Also, you got to remove the O and P object as well, right? So there will be a serious deletion you have to do. Let's just talk about one of them. How do I actually remove the vertex from the doubly linked list? Okay, part of the step. Will be to remove the doubly linked node storing vertex B's reference, which means we want to remove this one here. Right? You can see that in this doubly linked list, this is the node that stores the reference of vertex B. We want to remove it, right? So now we have a very good shortcut for us, because if I know the reference for vertex B, I know immediately what's the reference for this particular node, because I got the attributes. I can do it right away, right? So let's write down the code together, right? It's not rocket science, right? It's very straightforward. So I say the V, which is doubly linked list, and then we went over the remove method last time. Right? Over here, we're going to pass a doubly linked node reference. Now, how can we do it? Well, you got a vertex B right here. And then we know that that one there has an attribute called vertex list position. Right, there we go. So that removal in general is going to be constant time, very efficient. All right. So you will see this particular, this kind of like a bidirectional references for all the three strategies. You'll see them, right? They're very common practice. Okay. Guys, any questions about this? Okay, let me just say one more thing. Okay, so just to make it explicit, and of course, this remove over here, as we studied last time, is going to be big O of 1. Right? Very efficient. Okay. One thing I want you to, well, actually, you will be asked to do for assignment number 2. That one will take a little bit of like struggling just to get right. It's not too tricky, right? Edge list strategy. For your assignment number 2, some question will be, given a vertex, how do you compute all incident edges? So IE here will be incident edges. For example, if I'm given A right here, how do I know all the edges that's connected to A? Should be O and P and R. From the diagram, it's very easy. But how do we do that if we got data structure like this at the runtime? So that's something you have to work out for assignment number 2, right? Also, for programming test 2, you might be given something similar to this. All right, I think that's good enough. I think you definitely got all the background information for assignment number 2, right? The programming part. Right. Question? All good? Okay, good. All right, so that's about the edgeless strategy. I think sometime next week or the week after, we'll talk about another 2 strategies. So bear with me, right? We'll get there. But we definitely want to do something more exciting, shortest path, next week. Okay. So let's also give you a very quick brush up about what you learned back in 2030, maybe many years ago, right? Or maybe only last semester, I don't know. Or maybe, cannot be last semester, maybe 2 semesters ago. Okay, okay, so if you recall, in Java, right, AD OOP, if this supports exception and exception handling. So sometimes you want to call a method, there will be one scenario where you expect the exception to occur. But there might be another scenario you don't expect any exception to occur. You will see both scenarios in assignment number 2. Let me just talk about at the Java level how you're supposed to handle, right? Let me just enumerate all the scenarios you will see. You got to draw the connection to the actual assignments, okay? Let's say we have a method M, right? So Java keyword will be, you got to say, as part of the header for the method, you say that method throws some exception, right? And then somewhere in the implementation, you might say, if some error condition is true, I'm going to throw some new instance of some exception, right? That's something you learned back in 2030, right? And whenever you actually say throw something, right, some exception. So there is the so-called catch or specify requirements. But we wouldn't dive into it. We'll lose the focus for this course, right? Just if you're kind of interested about what this really is, you can look it up. I'm pretty sure your professor, could be myself or maybe somebody else, cover that. Okay? Let's see exactly how we can understand, just for the context for assignment. Okay? So we know that for this method here, it may or may not throw some exception, may or may not. All right? First of all, let's write down what we know. So for M here, may or may not throw some exception. All right? Similarly, this part here, just duplicate. I want to show you all the scenarios. This one here also may or may not throw some exception. Depend on the input. If you give some normal input, then exception shouldn't occur. But if you give some abnormal, like an illegal input, then you should really expect exception to occur, right? So the expectation can vary depending on how legitimate the input is. All right? So let's talk about two scenarios. Scenario number one. Let's say the exception is not expected. All right? Let's now work out the logic here. If exception is not expected, accordingly, if some exception occur, that means it's outside our expectation. So the test should fail. On the other hand, if some exception not occur, then there should be a pass scenario. Okay, let's go over again. Okay, very important. Let's say now my expectation is this particular exception is not supposed to be thrown from this method call. Not supposed to be. If it was thrown, then my pass should really fail to indicate there's some error with the implementation. However, if the exception is really not thrown, that's good. That's exactly within my expectation. So in that way, we should really pass. All right? Okay, we'll see exactly how to code it up, right? Just one moment. And let's now consider another kind of expectation. Okay? So let's say here, the exception is expected. Okay, so let me just write down something here that might help you. For example, not expected. For example, is legal input. And when we say it is not expected, it could be some illegal input. Right? So the input we are talking about over here could be just different. That's why we're expecting different behavior from the method. Right? So now let's work out the logic again. It will be just flipped. So let's say, for example, here, accordingly, if some exception occur. Now, in this case, should we pass or fail? Is it within our expectation or outside our expectation? Pass, right? It's exactly within, right? Thank you. All right, so that one should be pass. On the other hand, if some exception not occur, that means you should fail. So you can see that when the exception occur, one can fail, the other one can pass, depending on the expectation. So you got to make sure you read the test case very carefully. Otherwise, just don't know how to implement the stuff accordingly, right? So you got to make sure these kind of trick about programming the JUnit test cases are well understood. Okay. Oh, what about the actual test, right? We got to say how we can do it. Okay. So the way to do it is we have to make use of the fail assertion. Okay? That's also part of the JUnit library. Right here, we are saying that we are not expecting the exception. So let's say here, the exception is somehow thrown from here. That means it will be caught right here. So if we are able to reach this part of the code, so that means the exception happened unexpectedly, then we should fail. On the other, so that means if you're able to go this way, it will be the fail case. On the other hand, if you actually are able to go from this line to the next line, something like that, that means exception has not been thrown from that method call. In that way, it should be a pass, right? Some exception not occurred, pass. Pass in the sense that you just don't fail, all right? All right, it will be completely symmetric for the other one. Let's finish that for completeness. We're still making the same method call, but this input here is somehow illegal, right? Let's say we still go, the exception really occur, and then we are able to go to the catch block. In this case, it's good. It's within our expectation. So don't fail. Just leave it empty, right? So this will be basically right here. So some exception occur as expected. Don't fail. Just do nothing. On the other hand, if you're able to go from this line to this line over here, the execution flow actually continues without any disruption. So that means nothing exceptional occurred by calling the method. So what actually expected about the exception did not occur. So we should fail. Okay, we'll put a fail right here. Okay, the expected some exception did not occur. All right. All right, so make sure you understand about these these scenarios about expectation and also how you put the fail assertion, right? These are important, right? You definitely need them to see exactly how to implement your methods for assignment 2 and programming test 2 later. Okay. Questions? Okay? Okay, sounds good. All right, let's now move on. I would like to go directly to our second traversal for graph, which is breadth-first search. I'd like to go over that first principle and also do some tracing together. Hopefully it wouldn't take too long. And then for the rest of today's lecture, I just want to compare depth-first search and breadth-first search. Hopefully we can draw a nice conclusion, well, almost a conclusion for the two traveling mechanism. And then next week, we can start talking about shortest path, right? We're kind of building things gradually. Okay. So let's take a look at this slide here. So we talk about slide number 44, all right? So breadth-first search or BFS, okay? So for breadth-first search, we're only going to trace about undirected graph. So if you do directed graph, you'll be very similar. So luckily, if you do breadth-first search on directed graph, you don't really have to worry about like a back edge, forward edge, and cross edge. For breadth-first search, in either directed graph and undirected graph, there are only two kinds of edges, discovery and cross edge. But we're going to see them, right? But for depth-first search, you have to know which kind of graph you're really applying that to, right? Okay, well, we'll see those comparisons pretty soon. Okay. Okay, let's now look at some basics. Okay. Yeah, you guys can go over the slides on your own, but we're going to look at them together right here. Okay. So breadth-first search, and then it's going to also you're going to start from some vertex V. There's got to be some start vertex. Okay. Let's say, for example, we're going to start from A right here. Okay. Similar to how we introduced to you about depth-first search, we chose a very special graph just to do the first example. You can see this is a graph, but it's also a tree at the same time. There's no cycle, right? Just make things a little bit easier. When you got exactly just a tree, that means what you'll end up having will be discovery edges only, or tree edges only, okay? Similar to depth-first search, but we're going to see how you can do it. The order of visiting or identifying the edges will be different, okay? The principle will be here. you have to make sure, given a particular vertex V, you have to visit every adjacent edges, every adjacent vertices before you can move on. Okay? This will be the most important principle. Okay? So you can think about here, this part here, basically you follow the incident edges. Oh, you know what? Let me write down a little bit more appropriately. I'll put it here for now. Okay, I'll repeat it. Okay, so incident edges. Incident edges. Okay, and there's some intuitive analogy. So for depth first search, you want to go as far as possible. You keep extending the path until you have to backtrack, right? Or yeah. On the other hand, for breadth first search, you want to stay as close as possible. You don't really try to expand. You don't try to move away from the started vertex too soon. You want to stay as close as possible. You will see. Okay? There's no such concept about backtracking, okay? Luckily. So it's not too bad to keep track about what's going on. And what data structure we're going to use, okay, it's going to be a FIFO first in, first out queue. Okay? I'll write it down here, and then we'll do example. It's going to be a first in, first out queue. Okay? And let me write down the most important principle here. You got to make sure you remember when you actually try to do the tracing. Okay, I'll put it here. So if you have a queue, initially empty. A little bit of look ahead. So here we talk about the first in, first out queue. But next week, we need to talk about something called a priority queue, which is not exactly a FIFO queue, right? So if you are interested, maybe you want to brush up quickly about what a priority queue really is, as opposed to FIFO queue. We'll review anyway, but it might be nice for you to do a little bit of review yourself first, okay? So the principle will be, you only dequeue a vertex after, let's say vertex X, okay? After all X's adjacent, after all X's, I beg your pardon, I just made a typo here, incident edges are marked. And when I say marked over here, it could be either a discovery edge or cross edge. I'll put it down here, or cross. Okay, we'll see exactly how these will be marked very soon. Okay, great. Let's just try to do this one here. Okay, so we start with this vertex here. Okay, so now A, we'll start with it. In queue, A. So we put A in here. All right, before we can dequeue A, we have to mark all A's incident edges, okay? Which will be, again, we'll follow alphabetic order, right? We're going to go for B and C and D, all right? So that means B and C and D should be in-queued into here. At the same time, since all of them are unvisited at the moment, they should all be discovery edges, all right? So we got here, let me get a little bit thinner, B, C, and D, okay? So 1 and 2 and 3, okay? So we got B and C and D. As soon as all these edges are identified and also all these vertices that are adjacent to A have been in queue, we can now dequeue A. Okay? Before I do that, let's make some quick notes. Right? There's a very important visual observation you should really have about breadth first search. We're going to divide the graphs by layers or levels. Okay? So think about so far, we have 2 layers already. The star vertex A There's only one vertex at that particular level for the start vertex. So we call that level 0. Exactly how we divide the binary tree into different levels, if you recall, right? So now this tree will be like a general tree. We just divide the general tree into different levels. Similar idea. Level 0, level 1, level 2, level 3, etc. Okay? Okay, level 0 is here. And then what we just finished was level 1. Level 1 here. Okay, so let's now do that quick distinction. Think about A here was level 0. And B, C, and D that are adjacent to A, that's level 1. We're going to go level by level. Once we have covered the bottom levels for the tree, or somehow the bottom level for the graph, or the spanning tree that's going to be resulted in, then we are done. Right? Now, how do we extend? First of all, since we got B, C, and D already in the queue, and also all these edges have been identified, so now we can remove A, DQ. For this first example here, we're not really tracing exactly like the order, but you will see it will just follow nicely with the order we are putting. But I'll do that in the second example after the break. Okay. All right, so now what should we do? Similar to depth of search, you want to see what's at the top, the front of the queue. Front of the queue is now B. So now you have to treat the B almost like a current vertex to really handle, right? So from there, so far, all these 4 vertices have been visited, right? B, C, and D. All right. So now for B, we're going to go for all its adjacent vertices, which will be E and F, right? And both of them are unvisited. So this will be another 2 discovery edges. So we got E and F. So now we also visit them as well. At the same time, we're going to put E and F. Once this is done, we're going to DQ B. And then the front of the queue has now become C. So we go to C. For C here, there's no way for you to go any further. So C is done. You're going to remove C from the queue. And then the front of the queue has now become D. D also has nothing for you to expand any further to further level. Also DQ, D as well. All right, so now we are done with level 1. All right, and this will be number 4, this will be number 5, right? And you can think about this one here, E and F are level 2. Right here, level 2. Right, let's try to see how we can complete this. And these 2, level 2, will be E and F. Let's see if we can expand any further to level 3. Okay, so E will now be front of the queue. We can expand to G and H. So these are the 2 discovery edges. Okay, so we're going to expand further. G and H. So that would be 6 and 7. And we're going to visit these 2 nodes, G and H. And we're going to in-queue them to the queue. That's going to be G and H. All right? And then front of the queue is now G. But we cannot expand any further. Done. Remove it. And for H over here, we also cannot do any further, go any further to any further level. So that one also DQ. All right. Good. Yeah, E and F should have been removed already in previously. I just forgot. Right? Just make sure whenever you're done with this particular vertex at the moment, you have already identified all the incident edges, you really remove it right away. I'll make sure I do it more properly, more completely in the second example. All right, so after G and H are removed, so that means we are now done with the final level. Okay, so think about right here. This is level 3. level 3, level 3. Okay. And did you notice one thing here? How many edges do we have? 7, right? Go up to 7. How's that related to the number of vertices? Number of vertices, -1. How come? Because it's a spanning tree of this graph. All right, remember that property there, right? It's going to keep coming back, right? That property here. All right. Okay, let's write it down. So the discovery edges right here form a spanning tree. And the number of discovery edges, which is equal to 7, right? You can see 1, 2, 3, 4, 5, 6, 7, which is equal to the number of vertices, 1, 2, 3, 4, 5, 6, 7, 8, minus 1, right? That's a nice little property we studied, right, earlier. Right? Keep verifying the property we learned earlier in the lecture, all right? Okay. All right, we're about halfway through. Why don't we take a short break? And then after the break, I think we'll do one more example. Yeah, question?
Just going to ask, don't discovery edges always form a spanning tree?
Always.
Any non-discovery will be cross edge?
Yeah, okay, yeah, exactly. Oh, that's a good question. So yes, the definition for spanning tree from either depth search and breadth search are always containing discovery edges only. So you want to exclude those non-discovery. That's why discovery edges are also called tree edges, right? They form the tree. Good question. Yeah. All right, so why don't we take a short break? Okay. So let's do one more example for breadth search, and then I'll give you some exercise. I also got a solution ready on the lecture side. Let's talk about this one here. This is another slide just about what kind of edges you can mark when you do breadth search. It will be slide number 45. You can take a look, but let's now just visualize it very quickly. Okay. Right here. So you can think about, before the breadth search starts, let's say nothing has been visited, nothing has been marked. You keep it just empty, just unmarked, like a white color, a little bit like that. And when you want to, whenever you start with maybe some star vertex, as we did earlier, that's something we did exactly before the break, right? You're just going to go for discovery edge or tree edges, 1, 2, and 3. Okay. Oh, that's something maybe worth mentioning again. So discovery edge also is the tree edge as well. Okay, just make sure you understand they really mean the same thing. Okay. Question.
Are we still going to be dividing them into levels even if we're not using a tree for this example?
We're definitely going to divide them into level. You will see exactly. Because the example we're going to do, the second example, the graph itself has cycles. In that case, we're going to see not just discovery edges, but also cross edges. You can see we can still try to interpret the graph as different levels. We'll see. Yeah, good. All right, discovery edge, and then let's look at cross edge. This one's interesting. Okay. So here, from A, we can do B, C, and D. All right. Let me draw a little bit better. I'm pretty sure I can do that. A to B, A to C, and A to D. Right. And the front of the cube will now be B. All right, so now what's going to happen is we can now discover B to E. Actually, since we go alphabetic order, so B to C here, we're going to something that's already visited, right? Think about after we got all the 3 discovery edges, A here, B here, C here, and D here, they're all visited. So now the front of the cube is B right here. And we're trying to visit this and this. These are the 2 incident edges. Here, C here is going to be a cross edge. And then E here is going to be another discovery edge. It's going to bring us to level 2. All right? And then I think a cross edge. I think that'll be enough. You will see another kind of interesting distinction between cross edges. We'll see that in the example. Okay, what can we say about a cross edge? Okay, let's have some little notes here. you can think about over here the cross edge that we are talking about. They are basically connecting nodes at the same level. From this example here, you can see we are connecting B at level 1 to C also at level 1. However, it is possible a cross edge may contain nodes at different level. It's also possible. But for now, let me write down the nodes first. But you will see the example when we trace the second one. Okay? The same or the next level. Okay, we'll see exactly how. So there's a little typo which I'm going to correct on the slides. In the slides, we also say the same level. The more precise way to say it will be or next level. I'll fix it when I revise the slide and post it later. Okay, or next level. Okay, okay, either the same level or the next level. Okay. Okay, only two edges to worry about: discovery and cross. Okay, so it's going to be quick. Okay, let's do a second example here. Okay, let's do this one here on the retrograph. And the assumption is we are going to visit the adjacent vertices in alphabetic order. Okay, we're going to do that. Let's say the star vertex is A. Oh, vertex is A. All right. So now, as soon as we start, we're going to visit A. But let's now trace together with the Q and also the order of InQ and DQ just to see what's going on, right? So what we do is we got here, let's say that's our Q. Okay, so here would be the front, and here would be the end of the Q, right? Because normally I like to draw, the stack upside down, and then the Q will be horizontal. But if you prefer the other way, doesn't matter as long as you can do it. Okay. Okay, the front and the end. So now, first of all, we put A here in the Q. So now, front of the Q is A. What should we do? We should visit all the incident edges. Okay. We're going to visit in this order: B, C, and D. Okay. So far, so good. So we got B here, C here, and D here. That means we're going to visit B, C, and D in this particular order. That will also be the order to InQ as well. Okay, I'll draw the table. I just forgot. Okay, so here we're gonna InQ B and then C and then D. Let's set aside a table here. Okay, so we got InQ'd and DQ'd. Okay. Of course, we first InQ A, and then from A there we find the three discovery edges, and we're going to InQ B, C, and D. Right? That's where we are right now. So, as far as A is concerned, we have covered all the incident edges. So A should be DQ'd. And we're now going to look at, just before, also we can also say 1, 2, and also 3. You can think about 1, 2, and 3 are the three edges that will lead to three vertices at level 1. Okay. And if you like, we can also do this. A here is level 0. So A here is level 0. Okay, and B, C, and D right here will be level 1. Actually, this might be a better. Okay. Okay, this will be level 1, level 1, level 1. All right. And from every node in level 1, we're going to see how we can expand to level 2. Okay. So for the front of the queue, right now, it's B. And B here, we should really do alphabetic. We should really go for A, C, and E. A is already marked, so don't worry. Okay? So we got to go to C first. C has been visited. It's a cross edge connecting to a node at the same level, right? So this one here is a cross edge. And that one there will be number 4. And then we go for the next incident edge, which will be E. That should be discovery edge because the target vertex is unvisited. Good. So that one will be here. And that should be number 5. Okay. So that would mean E here should now be in Q. Right? And E is now visited. Okay. So now you can see as far as B is concerned, we have done with all these incident edges. So B should go away. Okay. So we're going to DQ B. All right. What's next? We should look at front of the Q, which is C. All right. So now for C here, interesting. C here has 1, 2, 3, and 4 incident edges. C to A, we don't need to. It's already identified. C to B, cross edge to the same level. C to D, cross edge at the same level, right? Okay, so now we're done with A, B, and D. What about C to E? Is it discovery edge? Cannot be, because E is visited. That's also a cross edge. But this cross edge is connecting to the next level. That's exactly why I said it can be next level. Okay. So here is going to be another cross edge. Okay, so the order will be 6 here, and also 7 here. All right. So now as far as C is concerned, oh, actually C can also go to F. I forgot about that, right? So you can see C can also go to F. That will be discovery edge, right? All right, so that one there is going to be number 8. Okay, number 8 here. And then that one there, we're going to inQ F. So that means it will be visited right here. All right. So now C here, you can see we have handled all the incident edges. So it can be DQ'd. By the way, we say DQ, we don't say backtrack. Don't confuse the term. It's not called backtrack. All right, so here, C is gone. What about D? For D here, 1, 2, and 3 incident edges. But these 2 are identified already. Ignore them. How about this one here? Cross edge, right? It's visited, right? To the next level. Awesome. All right. I think you guys got the basic, which is good. And then I'll give you some nice exercise to try. Okay, cross edge. All right. That's good. So D is now done. C is in DQ first. I just forgot to put it, right? C and D are done. So you can think about, as far as level 1 is concerned, B, C, and D are done in the sequence. First in, first out. And we got to handle level 2. Okay? Think about E and F here is really level 2. Okay, so this part over here will be level 2. So E and F will be level 2. Okay, like that. And then the front of the Q is E. both incident edges are covered, DQ. And for F, also both incident edges have been covered, has been identified, right? Also DQ. And the queue is now empty, we're done. All right, let's make some very quick notes so that you will just remember that property, okay? So think about these two. So this one here and this one here. That one is the cross edges connecting nodes at the same level. On the other hand, you can think about this one here and also this one here, okay? Those are also cross edges, but they will connect the nodes at different level, connecting from level x to level x plus 1, basically, okay? Connecting nodes at different levels. Right? It's important to understand about the two possibilities, different levels and also same level. Okay. Guys, questions? Yes?
If you're given a different node to start, will the levels change?
Ah, very good, Diago. That's a very good question. That's exactly what I wanted you guys to do. Okay. So let's say, for example, right? Let's give it a try. Just hand wave a little bit, if you don't mind. Let's say this one here, the same graph, right? Let's say I start with here. Oh, how about we do a little bit? Actually, let's do it. Otherwise, you might just get confused. If I do this one here, I start with here. Okay, let's say. And then that one there is going to go to A, C, and F. Agree? So now you have to use your imagination. The tree, spanning tree that we are building, this one here should be level 0. And this one here should be level 1. All right, good? Okay, you see the idea. Good. So this part here will be level 0. And this part here, A, C, and F, will be level 1. And of course, level 2 will be the remaining 2, right? So yes, the start vertex definitely is going to change the shape of the spanning tree. But the number of edges in the spanning tree you're going to get will be the same. It's going to be the number of vertices minus 1. Yeah.
So basically, if we were to implement this strategy, we just need to count the number of incident edges until you get to your starting point to know the level.
Kind of, yes. So if you somehow want to know which level you are, you definitely have to keep a counter, when you do it. We will see, maybe in the actual assignment. Yeah. Mm-hmm.
And then my second question was, are we also going to use a similar timetable to what we use for...
Good question. Luckily, for breadth-first search, you don't need a timetable. You don't need to, right? So I think for the breadth-first search, it's going to be very straightforward. You're just going to worry about discovery edges and also cross edges. I would say, as you pointed out, in this particular case, the level is kind of divided not exactly vertically like a normal tree. You have to use you can see exactly, right? So the exercise I'm going to assign to you guys is complicated enough. I think you really want to dive into it, okay? This one here, all right? This one here, and I want you to, let's say start with A. For example, let me help you a little bit. Level 0. Level 1, go to B, and then E, and then F. Level 1, and so on, right? Use the queue, and then to follow up. It may not be as straightforward as you might think. You definitely need to practice that and identify the cross edges, okay? Where can you find a solution, okay? On the lecture site, you will see that under exercises, tracing BFS by FIFO-Q, right? You can see the YouTube video. If you only want to see the final outcome, for example, that's okay. Videos there. If you want to watch them, it's really to your benefits. But if you just want to see the final outcome, just go to around the end of the video and take a snapshot. and then you can get a solution as well. Yeah. Okay, I'll leave this resource to you, so you can choose whatever way you feel comfortable of using it. Okay. All right, so that's about breadth search. Okay, about how you can trace it using FIFO queue. Right? Start vertex will be very important, and also about the order in which you kind of visit the incident edges is also very important. Right? Could be alphabetic, or could be some edge will take some priority, right? Like what we did for the depth search. Okay. We got about 15 minutes or so. I think I can cover some comparison about the depth search and breadth search. Let's do a little bit. I think I may have to leave some of them to choose Monday. I'm pretty sure we can finish that before the first half of Monday, and then we'll talk about weighted graph and also Dijkstra. It's going to be lots of fun. Okay? Also looping variance, okay? Things like that. All right, let's now do one by one. Okay. By the way, so now I'm not telling you which one is depth search, which one is breadth search. Are you able to tell just by using the diagram? Pink one are discovery edges, just in case, right? Diego, which one will be the depth search?
The one on the left.
The one on the left? How come? Justify a little bit.
Yeah, because the discovery edges are going from A to B and then B to C.
Exactly.
You just keep going until.
Yeah, go as far as you can. Versus, if you're actually trying to do, for this one here, you basically go for all the incident edges. You can immediately tell. So that could be a nice, maybe a written test question. For exam, I'm not too sure, because usually it's black and white, unless I have a way, to really visualize it, Anyway, so that's a nice question you can expect. Not exactly the same, but something similar, okay? All right, so we agree that this one here is depth search. And this one here is breadth search. It's not really the focus for this page here, but let me look ahead a little bit. Let's say this is the whole graph. All right? Is this graph connected? No. How many connected components do we have for this graph? 2. 1 here and 1 here. So this means when you got more than one connected components, you will need more than one depth search or breadth search run. Meaning that when you actually, maybe that's not for assignment 2, assignment number 3. Well, one of the common graph questions you want to ask would be, how many connected components do I have in the graph? How can I figure out? You can either use breadth search or depth search. You arbitrarily pick one unvisited vertex and do a, let's say, depth search. If that one there can visit all the nodes already, you know that the graph is connected. If no, you have to somehow use a loop to make sure keep looping until you cover all the vertices. I'm going to write it down, don't worry. I just want to talk about it first, okay? Let's talk about runtime in general, okay? So the runtime for depth search and breadth search, they're consistent, right? Any efficient implementation should be, okay, I'll write it down, and then we'll talk about it. So let's start with the running time of depth search or breadth search. The big O of, so now let's revisit about the two mechanisms. For depth search, we use the last in, first out stack. We said many times, every vertex is going to be push and pop only once. Every edge is only identified as one kind, right? Similarly, for breadth search, you actually try to use a queue. Every vertex is actually in queue and dequeue only once. And also, each edge is either cross edge or discovery edge. There's no third possibility, right? So any efficient implementation, you can expect that the running time will be just proportionate to how many edges you have, how many vertices you have, right? So that will be the running time. But there will be some assumption we are making. I'll write it down as well. Okay. It will be n plus n. M here will be the number of vertices. N here will be the number of edges. So it's really proportionate to how many, the measure about how many edges you have and how many vertices you have, right? Yeah. But we'll see later, it's interesting because sometimes one measure can dominate the other. Can you see why? Sometimes we may not need to say n plus n. We can say something that's because one can dominate the other asymptotically. It has to do with some of the property or particular graph we talk about. Let's talk about it very quickly, right? I'll give you a hint. What's the upper bound for number of edges? The number of vertices? Minus one? No, you're talking about spanning tree. I'm talking about upper bound for the number of edges in a graph. Around n squared, in which case we call that a complete graph, right? So now imagine that in the case of the complete graph, this one here will be, this one here will be n, this one here will be about n squared. Adding up together, still n squared. Okay, I'll write it down. Okay. If the graph is complete, you will end up having n. I think I kind of mixed some inconsistency. Okay, let me fix it right away. I believe we said n should be number of edges and n should be vertices, I believe. Okay, I beg your pardon. I'm pretty sure that was the case, right? Sorry about that, okay? So here, if a graph is complete, it's going to be number of vertices will be n still, but number of edges will be n squared. So we can reduce that to big O of n squared. However, this is only true if you know the graph is complete. Otherwise, you cannot make such simplification. All right? Okay, I think also it's a nice thing to see right here. Okay, so what's the assumption about this particular running time? We're assuming that because for both the depth first search and breadth first search, let's say from here, A here, we want to know what's the incident edges from A. We know that it's going to be A to B, A to C, A to D, so we will know which one will be visited, which one will not be visited. So there's got to be some efficient way to calculate your incident edges or to even go there, right? We're assuming that's such efficient implementation, okay? And I'm going to write it down here. That one will be something you will see even more once you have done with assignment assignment 2. Okay, so the big O here, assumption. Accessing a vertex incident edges, i.e. incident edges, is big O of 1. However, the edge list that we learned so far is not big O of 1. That's why it's not as commonly used, but it's very good for pedagogical reason. We should really see how that one works, and we'll see immediately how the adjacency list will work. All right? Big O of 1. Not the case for edge list. Strategy. All right, not the case. All right, let me write down 2 more notes, and then we can do maybe 1 or 2 more properties, and then we're done for today. Okay, so for depth first search, each vertex push or pop only once. Similarly, for breadth first search, each vertex inq and dq. Only once. All right. We'll see later how to use this running time here and develop that a little bit further when we talk about the Dijkstra algorithm. Okay, later. Okay, but it's good to get this foundation understood first, and then we'll build on that on top of that later. Okay, let's talk about connected components, which I kind of hand wave a bit. Let's now make it more visual. Okay. Again, we got depth first search, we got breadth first search. Let's say here. So we got depth first search right here. We got breadth first search over here. Okay. If we start with A over here, you can see that after the first run of the DFS, what we can get would be this part here. Similarly, if we do breadth first search after the first run, this is what we will get. So that means, in general, if I don't tell you that the graph is connected, it's not exactly correct. When you say, once I have done a breadth first search or depth first search, I'll get a spanning tree for the whole graph. It's not correct. So what will be the correct way of saying it if I don't tell you anything about if the graph is connected or not? For example, you can see that these two graphs over here, they are not connected. So if I say, for example, after doing this depth first search over here, I say the spanning tree I have is a spanning tree for the whole graph. Obviously, that's wrong. What would be the correct way of saying that? Go ahead. Say it a little bit louder. Connected component, well, okay, that's good. I like it. So what Jada says so far is it's a spanning tree for the connected components. But I got connected component number 1. I got connected component number 2. Which one are you talking about? The first one. But how do you qualify the first one? Huh? What do we know about the first one? It should be the connected components containing the start vertex. Okay, that's the way, okay? Let's write it down. Okay, so think about this is connected component number 1. This is connected component number 1 as well. Okay, so let's now draw some common conclusion right here. Right, if you look at these. Okay. In general, A, DFS, or BFS gives the spanning tree of the connected components containing the start vertex. Right? You ought to understand every part for this statement here. It's so important. If I didn't say if I only say connected component, it's simply unclear about which connected component you're talking about. It ought to be the one that contains the start vertex. All right. And if I do, let's say, another second depth first search, it's going to be a spanning tree for this particular connected component containing this particular start vertex, right? So depending on what the start vertex is. What if the graph is connected? Let's say there is an edge. Let's say there's an edge right here. This statement here is still true because there's only one single connected component in the connected graph. In that way, after doing the depth first search, we're going to cover all the vertices, right? So it still holds. So this will be the most general statement to make, even for unconnected graph. Okay? So in general, not assuming the graph is connected. Okay, good. And then let's see over here. So this will be connected components number 2. And of course, if you do a second breadth first search with a different start vertex, this will be connected component number 2. Right? Just put them in side by side. Okay. Let's write down some notes right here. Okay. The graph here is not connected. the whole graph. That implies, number one, we got more than one connected components. Number two, more than one DFS or BFS needed to visit all vertices and edges. All right, very important concept over here. Okay, we got about 1 minute. Okay, how about this? This one without me writing down, okay? Let's say this. Okay, 1 minute. Your assignment number 2 kind of asks you about to implement depth search, I believe. So now, let's say, how can you, let's say I have the method there called DFS. I can call that with some start vertex and you will do whatever depth search is supposed to do. Having this method here, how can I write some fragment of code to make sure if I am given some graph that's not connected, you will actually always try to do as many depth search as possible, well, as needed. Just talk about the idea, and then we'll write it down, maybe on Monday. Yeah, go ahead.
You have a while loop that runs a helper function, and the helper function looks through all the listed vertices and checks to see if all of them have been visited.
Yeah, exactly. So what we're doing is you can maybe have a counter. So every time you're visiting a new vertex in the depth search, increment by 1. Keep incrementing until you can reach to the cardinality of capital V, right? All right, for this one here, I'm going to write it down on Monday. All right, thank you so much. I'll see you guys in Willis Small Center tomorrow. Okay, see you.